In this work, we focus on the cooperative manipulation of mechanisms by dual-arm robotic systems. When interacting in a human-centric environment, mechanisms are commonly found as doors and drawers, and several tools consist of simple mechanisms. In addition, many assembly tasks can be modeled as mechanisms with one or more degrees of freedom. We focus on manipulation under geometric uncertainties. When all the relevant geometrical information of a given manipulation problem is known, the task is relatively easy to accomplish with traditional methods. In unstructured environments, however, an identification method is required in order to determine the properties of a mechanism. These are the direction of the available degrees of freedom and location of the mechanism's joint. We model a 2 degrees of freedom mechanism, composed by 2 rigid objects connected by a joint. We assume that one of the available degrees of freedom is translational, and the remaining degree of freedom is assumed to be rotational. Assuming these assumptions, we derive a kinematic model of the mechanism in terms of relative motion between its rigid parts. The derived manipulation task is integrated in the extended cooperative task space network, which decomposes the motion of a 2-manipulator system into absolute and relative motion. Furthermore, it allows the user to choose the degree of contribution of each manipulator to the relative motion task. The absolute motion task consists of the motion of the 2 manipulators along the same directions, while the relative motion task is defined as the difference in motion of the 2 manipulators and effectors. Our manipulation task is defined in this space. To identify the geometric uncertainties, we rely on the force and torque sensing. The contact location between the mechanism parts is assumed to be the location of this joint. We rely on the relationship between torque and force at the end effector to identify this location, using common filter estimator. The degrees of freedom of the mechanism are estimated with an adaptive algorithm integrated with the control law, which defines the reference velocities for the manipulation task. We implemented the simultaneous manipulation and identification algorithm in a PR2 robot, equipped with one force and torque sensor. The manipulation task is shared evenly between the 2 manipulators, and sinusoidal motions are commanded on the 2 motion directions. After an initial transient, the estimates converge to a close vicinity of the real values. Future work will focus on exploring the identification of uncertainties with a 2-sensor setup and studying on how the degree of collaboration between arms can be explored to improve the estimation results.